Hi, thanks for joining me. Today I'm really excited for this video because we're introducing a function which I don't think I've ever used before on this channel. It is the decimal digit product function. This problem comes from the Imperial College Maths Competition. Let's firstly see what this problem is all about. So let n be a non-negative integer. Firstly, we define the decimal digit product d of n inductively as follows. So if n has a single decimal digit, then d of n equals n. So for example, d of 3 is just going to be 3 because 3 is a single digit integer. Otherwise, we let d of n be d of m, where m is the product of the decimal digits of n. So for example, d of 325, this would be d of 3 times 2 times 5. And now 3 times 2 times 5 is 30, so this is going to be d of 30. And now 30 is not yet a single decimal digit, so I use this again. So this is just going to be d of 3 times 0. And now 3 times 0 is just 0, so d of 0. Now this is a single digit, so I get 0. So d of 325 is 0, for example. And if I just do another one, d of 284, this is going to be d of 2 times 8 times 4. 2 times 8 times 4 is 64. So this is d of 64, and now 64 is not a single digit, so I continue with this. D of 6 times 4, and that's going to be d of 24. Well, 24 is not a single digit, so it's going to be d of 2 times 4, and so that's going to be d of 8, and now 8 is a single digit, so I get 8. So that's how we define the decimal digit product function. Now, for this problem, we're going to say pk of 1 is the probability that d of I equals 1, where I is chosen uniformly randomly from the set of integers from 1 to k inclusive, whose decimal digit products are not 0. So almost uniformly between 1 and k, but we take out any numbers between 1 and k whose decimal digit product is 0. And what we want to do is compute the limit as k goes to infinity of pk of 1. Okay, so I'll give you a moment to digest this problem, and if you want, pause the video now and give it a go for yourself, and I'm going to dive straight into a solution. Okay, so the solution to this problem is really nice. We start with a lemma, we prove that lemma, and then we kind of just put together some ideas and use a very nice limiting argument to calculate this probability. So we're going to start, as I say, with a lemma, but just before I do that, I'm going to introduce a set S. And this set is a nice set. It has 1 in it, it has 11 in it, it has 111 in it, 1111 in it, and so on. All the positive integers whose decimal digits are just 1s. Okay, and I'm also going to introduce another function here, p of n. And p of n is very similar to d of n, but it's just going to be the product of the digits of n. So for example, p of 725 would be 7 times 2 times 5, which is 70. And how this differs from d of n is, remember, with d of n, I keep kind of taking the product of the digits of the result until I'm left with a single digit number. Okay, and so now I can state my lemma. So what is my lemma? And I'm going to combine these two things together. I'm going to say n is in S if and only if p of n is in S. So if I take a number n and it's in S, then p of n is in S, and also vice versa. If p of n is in S, that means that n must have been in S. So let's prove this lemma. So going from left to right is pretty straightforward. If n is in S, then n is a positive integer whose decimal digits only consist of 1s. So if I take the product of the digits, p of n will just be 1 times 1 times 1 times 1 and so on times 1, and that of course is 1, and 1 is definitely in S. Okay, so that's nice and straightforward. The reverse direction requires a little bit more work, so we're going to suppose that Pn is in S, but n isn't in S. So suppose, for contradiction, that Pn is in S, but n is not in S, and we want to show that this gives us a contradiction. Okay, well, P of n is in S, so we're just going to call P of n, whatever number it is, m. And so m is just the product of the digits in n. And so because, base 10, there are only 4 prime numbers between uh, 0, well, between 0 and 9, 2, 3, 5, and 7, we know that m is going to be a product of those. So m is the product of the digits in n. And so then if we look at the prime factorization of that number, we know it's going to be 2 to the power of something times 3 to the power of something times 5 to the power of something times 7 to the power of something. So 2 to the power of a times 3 to the power of b times 5 to the c times 7 to the d. And now we know that this number m is in S. So that tells me straight away that a has to be 0. Because if a is at least 1, then that means that my number m would be even. But you can clearly see that every number in S is odd. So this tells me that a equals 0. And very similarly, I can also get that c equals 0. Because if c is at least 1, then I know that my number m is a multiple of 5, and that means it should end in a 0 or a 5, but clearly there are no numbers in S which end in a 0 or a 5. So that tells me a and c are both 0. And now what we want to do is prove that b and d are also 0, but this requires a little bit more work. Let me clear up the whiteboard and we'll prove that. Okay, so we have that m is this guy here, and a and c are both 0. So now we want to prove b and d are both 0. And the way we're going to do that is by considering the elements in S. And if we just write them out in a sequence, so we start with 1, then 11, then 111, then 1111, then 11,111, and so on. What I'm going to do is consider this sequence modulo 3. So in other words, if I look at these numbers here and I just care about their remainders when I divide them by 3. So 1 modulo 3 is just 1. 11 modulo 3 is 2, because if I do 11 divided by 3, I get remainder 2. 111 divided by 3 gives me remainder 0. 1111 divided by 3 gives me remainder 1. And in fact, if you just do a few terms of this, you can see you get a pattern 120, 120, 120, and so on. And you can prove that this pattern continues by basically going, well, to get from one number to the next, you have to multiply by 10 and then add 1. So to go from this to this, for example, I have to do 11 times 10 and add 1. So I can do the same with the modulos. So to get from 2 to the next number, I have to do 2 times 10, add 1. And now 10 is 10 is 1 mod 3, so it's just going to be 2 times 1 plus 1. And so basically all I have to do is add 1 to my previous number, modulo 3. But anyway, you get this pattern 120, 120, 120. And now what does this tell me? This tells me that if I have m being a multiple of 3, so in other words, if b is at least 1, sorry. If b is at least 1, then m is a multiple of 3. But if m is a multiple of 3, remember m is in my set S, so it's one of these numbers on this list, and therefore for it to be a multiple of 3, that means it must be 0 modulo 3. And therefore we can see that the only zeros occur at every kind of third position. And so therefore m would have to be either 111, 111,111, oopsie, that's not that one, that would be the next one, 111,111, or the number with 9 ones in, or the number with 12 ones in, and so on. So let's say m was the one with 12 ones in. So m is, well, there's 111 billion, 111 million, 111,111. Now, there's nothing too special about this number. The only fact we're going to use is the fact that this is very clearly a multiple of 111. But because it's a multiple of 111, it also means it's a multiple of 37. Because 111 is just 3 times 37. But this is a big issue, because m can't be a multiple of 37, because m has to be just the product of 2, 3, 5, and 7. And, you know, if we looked at the prime factorization of m, we know it only contains 2, 3s, 5s, and 7s, and so therefore can't contain a 37. Therefore, b cannot be bigger than or equal to 1, so b has to be 0. Which is quite cool. So we now have a is 0, b is 0, c is 0. The last thing we need to do is prove d is 0. And to do this, we use a very similar piece of logic. If we look at these numbers modulo 7, we now get a similar pattern. We get 1, 4, 6, 5, 2, 0. And then it repeats 1, 4, 6, 5, 2, 0. And so on. And again, you can prove that this pattern repeats by just noting how you get from one number to the next. You multiply by 10 and then add 1. So modulo 7 multiplying by 10 is the same thing as multiplying by 3, and then you just go from one number to the next by multiplying by 3 and then adding 1. And we know that that's going to be a periodic sequence. And so we can see if D was at least 1, then M would be a multiple of 7. But if M is a multiple of 7, that means M is 0 mod 7. So we're looking for these guys here. And we can see that the zeros only occur at every 6th position. So that tells me the number of 1s in M would be a multiple of 6. So then, we know M, because it's in S, it just has 1s in it. So, and we now know that the number of 1s in S would have to be a multiple of 6. So maybe it could be 111,111, or maybe it could be 111 million, a billion, 111 million, 111,111, or whatever. It has to have, the number of 1s in it has to be a multiple of 6. But again, we get the issue that this has to be a multiple of 111, and therefore a multiple of 37, and that's not allowed because we know, we know the prime factors in it have to be 2, 3, 5, and 7. And therefore D cannot be at least 1, and therefore D is also 0. And therefore we get that M equals 1. But this is a contradiction because we're assuming that N is not in S, and we're assuming that N is not in S, and therefore it contains a digit that isn't 1, but therefore it's very clear that Pn cannot be 1. Because if you're multiplying a bunch of positive integers together and you get 1, that must mean that they are all 1. And that is our contradiction. And therefore, if Pn is in S, it follows that N must also be in S. Great, that proves our lemma. Now we're one step closer to proving our main result. Okay, so we're at the home stretch now. We just want to use this lemma here to compute this probability. So firstly, our lemma was all to do with P of n, but our probability here is to do with D of n, but thankfully they're nice and related. So D of n, remember we're doing the product of the digits of n, and we kind of keep iterating this process until we end up with a single digit number. Whereas with P of n, we only do this process once. So we just multiply the digits of the number, and even if that number is not a single digit number, we leave it there. So D of n is simply going to be P of a bunch of times of P of n. So in other words, if we do P enough times on n, we're going to get a single digit number, and that will be precisely D of n. Okay, and why is this useful? Because then because this probability here is all to do with when D of n is 1, I can say D of n is 1. That implies that if I do P sufficiently many times on my n, I get 1. And if I use my lemma now, because 1 is in S, I can kind of keep applying this lemma, however many P's there are inductively, that many times, to get that therefore n is in S. So if D of n equals 1, that means that n has to be in S. And it's quite clear to see that the reverse is true. If n is in S, then remember we know that n just has all digits 1 in, so D of n is very clearly going to be 1. So we get the fact that D of n is 1 if and only if n is in S. Great. D of n is 1 if and only if n is in S. So now we can go back to this probability up here. So we want to know the probability that D of I is 1, where I is chosen uniformly randomly from the set of integers between 1 and k inclusive, whose decimal digit products are not 0. And so to do this, I'm going to change this k here to 10 to the k, and the argument is essentially the exact same thing, but it's nice and it's much easier to explain with 10 to the k here, because if we think about how we define this set S, it's just got all the positive integers whose digits are just all 1s. So we now know that D of n is 1 if and only if n is in S, and therefore for D of I to be 1, we need I to be in S. And now if we're choosing I to be uniformly between 1 and 10 to the k, the numbers between 1 and 10 to the k, whose decimal digit products are not 0, we'll call that set tk to begin with, we know that the probability that D of I equals 1 is simply going to be k divided by tk, or the size of tk. Why is that true? Because there are precisely k numbers k numbers in S which are less than 10 to the k. And those are the numbers 1, 11, 111, and so on, all the way up to the number with all ones in where there are k of them. So all of these numbers here are less than 10 to the k, but if I looked at the next number up, so the number with k plus 1 ones in, that would be bigger than 10 to the k. So this has k like options. So for d of I to be 1, there's kind of k choices of numbers there. And so the question is, how big is tk? And we want to show that, so the probability that di equals 1 is now equal to k divided by the size of tk. And I claim that this probability here tends to 0. So I don't actually need to worry about the exact size of tk, I just need to show that it's sufficiently big. And so to do that, let's examine tk and the numbers that I know for sure are in tk. So tk is going to contain a bunch of numbers in it, but in particular it's going to contain the number 1. It's also going to contain the numbers 12 and 21. Because if I look at 12, the decimal digit product of 12 is 1 times 2, which is 2. Same holds for 21, and 2 is definitely not 0. I can also include the numbers 112, 121, and 211, because again, the decimal digit product of each of these three numbers is 2, and 2 is not 0. I can do this for 4-digit numbers as well, so 1112, 1121, 1211, and 2111. And again, these four numbers, their decimal digit product is not 0. And I can keep doing this until I hit the k-digit numbers. So the number that's like a bunch of 1s and ends in a 2, so there's k digits there, all the way through to the number which begins with a 2 and then has k minus 1 ones after it. So k digits in total. And so I know that tk is certainly going to contain each of these numbers, because the decimal digit product of each of these numbers is 2. Oopsie daisy. 2, well, except apart from the first one, which obviously is 1. If I want, I can change that to 2. And the question is, how big is this set on the right hand side? Well, it's got one element which is 1 digit long, 2 elements which are 2 digits long, 3 elements which are 3 digits long, and so on all the way up to k elements which are k digits long. So I know that this set on the right hand side has this size here, and this is very famously k times k plus 1 over 2. And therefore tk, or the size of tk, has to be at least k times k plus 1 over 2. And in fact, it's not too difficult to prove that tk must be much bigger than this number, but for the purposes of this problem, that's all we need, that tk is at least k times k plus 1 over 2, because now I can plug that in here and say this probability is less than or equal to k divided by k plus 1 over 2, and this number here tends to 0 as k tends to infinity. So, oopsie, the probability that this di is 1, it tends to 0 as k tends to infinity, and therefore pk of 1 tends to 0 as k tends to infinity, and that solves our problem. I hope you have enjoyed this problem. I really enjoyed this problem, and I think the solution is quite neat as well. If you are new to the channel, please do consider subscribing, and if you've watched this video this far, hopefully it means you have enjoyed it, so please do hit the thumbs up button below. It means a lot to me, it's completely free, and it really helps support the channel. Anyway, comment down below what you'd like to see me solve next if you've come across any interesting problems, and apart from that, I'm going to stop waffling. I will catch you in the next one. Have a great day.